Okay, in this session, we're going to look at purifying organic compounds. It's not the end of the organic chemistry topic at the moment, but it's just where this one fits in. And it is a practical skills topic. So we're going to talk about a lot of different practical skills that you might use and that you need to know how to do and carry out. So when we synthesize organic compounds, it's not actually as simple as we make it sound. Often we're like, oh yeah, just do this under reflux, or we just mix these two together and you get this. When we actually, the general thing that happens when we make organic compounds is the products, when we go through these organic reactions, are almost always full of impurities. It's never these pure products we get at the end. So actually we need to purify the organic compounds that we make. But there's lots of different ways that we can purify them, which we are going to look at now. And then once we've gone through the different ways of purifying them, we'll look at a couple of exam questions based on purifying these organic compounds. So the first one is separation. Separation is one that you'll have heard about a lot, and we're going to look at that in a bit more detail now. Now, separation, importantly, when we talk about separation, we are looking at water-soluble impurities. So that's really important to note, that we're looking at water-soluble impurities. That's the first piece of information. So if your product is insoluble, so if our impurities are soluble, our product needs to be insoluble. Otherwise, separation in this process will not work. So if we have got an insoluble product that's insoluble in water, then we can use separation to remove any impurities that do dissolve in water. So that's the idea of separation. So what we do is, once the reaction to form that product is complete, we go through the reaction, we've got the product, it's completed. We then pour the mixture into a separating funnel, which is what you can see here on the screen. And then into this separating funnel, we add water. So water is added to this separating funnel. So the first thing we do is we add the product to the separating funnel. And we add water. The next thing we do then is we shake the separating funnel. So we shake the separating funnel. And what will then happen is, because we've got a mixture of soluble impurities and insoluble product, is once we've shaken the funnel, we will allow it to settle. And when it settles, we will get an organic layer and then an aqueous layer. And in the aqueous layer, that is what's going to contain any water-soluble impurities. So this aqueous layer is that one that's going to contain some water-soluble impurities. And they are immiscible. So these two do not mix, they don't mix, and that is because they are immiscible. And immiscible means that they do not mix. So they are able then to separate into two distinct layers. What you can see on this separating funnel is it has a tap at the bottom. And then what we can do is we can open the tap that's at the bottom, and we can run off each layer into a separate container. Open tap, and we run off the layers. And that's the basics of separation. So for this example that we've got on the screen, the impurities would be run off first. We would then reclose the tap, and then we would collect the product into a second container. This process I've just shown you only works, I'm going to reiterate that, if your impurities are soluble and your product is insoluble. If our product and impurities are both soluble in water, there's a different separation method we can use. So we wouldn't use this one. So this is only when we've got products that are insoluble and an aqueous layer with impurities that are soluble. If both our impurities and our products are soluble, we can use a different separation technique. And the separation technique we can call, it's very similar, but it's called solvent extraction. So for these ones, we would use a separation technique that is called solvent extraction. What we do is we take an organic solvent in which the product is more soluble than it is in water. So we get an organic solvent. And the key part of choosing this organic solvent is that the product needs to be more soluble than it is in water. So organic solvent, which the product is more soluble in. And what we do is we add it to the impure product solution. We shake it well, and the product will dissolve into the organic solvent. And so what should happen is, I'll write that down again, our product will dissolve into our organic solvent. And what it will do is it will leave the impurities dissolved in the water. So our impurities are left dissolved in the water. And then the solvent containing the product can then be run off using a separating funnel, as we've just talked about. So that is one way we can remove water-soluble impurities from a product. If we're using this method, we have some issues with it though. So when we need to remove water from the purified product, because what's going to happen is if we're using separation to purify a product, our organic layer, so this product layer, is going to end up holding some trace amounts of water. So our product is going to have some trace amounts of water. That will stop it from being as pure as we would like it to be. So what do we do in this situation? We're going to dry it, so it is dried. So how do we dry it? It's not just as simple as just leaving it out to dry. We can, but there's a lot of different things that we can do. So to do this, if we were going to dry it, what we're going to do is we're going to add an anhydrous salt. So we'd add an anhydrous salt. So an example would be magnesium sulfate. Or another example would be calcium chloride. And this salt is used as a drying agent. And what it does is it binds to any water present to become hydrated. So it works as a drying agent and it binds to any water to become hydrated. What will happen is when you first add this salt to the organic layer, it will clump together. So it works as a binding agent and it will clump. And you'll see a clumping together of the organic product. And what you would do is you would just keep adding and adding and adding this drying agent until it disperses evenly when you swirl the flask. And then your final process would be you would filter. You'd filter the mixture to remove that solid drying agent. So we want to remove the drying agent. All we would have to do is pop a piece of filter paper into a funnel that feeds into a flask and pour the mixture into the filter paper. You can use a fluted, which is one of those concertina folded filter papers to increase its surface area. That's all you have to do. If you are then left with any other impurities other than water, what you can then do is wash. So any other impurities left, you can get rid of those by washing. So the product of a reaction could be contaminated with leftover reagents or unwanted side products. And so you can remove some of them by washing. And what we mean by washing is adding another liquid and shaking it. So for example, you could add sodium hydrogen carbonate. And we can add this to the impure product in solution to remove, and what this would remove is that would remove any acid from the impure product. The acid will then react with the sodium hydrogen carbonate and would give off CO2 gas, and then our organic product can be removed then using a separating funnel like you can see here. So sometimes you need to purify some of it before. So that's one way we can separate and remove water-soluble impurities, and even water-soluble impurities when your product's water-soluble as well. Another way we can purify an organic compound is through distillation. You've looked at distillation before, but we're going to look at it again. It comes up with loads. So as you know, distillation separates out liquids that have different boiling points. So when we're going through distillation, it's really, really important that we know the boiling points of the different products that we're trying to separate out. Distillation works by gently heating the mixture in the distillation apparatus. And what should happen is the substance will evaporate out of the mixture in order of the increasing boiling points. So just going to talk through this image here, just to give a quick overview of distillation, because we do know this. So we connect a condenser, which we can see here, to a round bottom flask, which contains our impure product in a solution. So this is our round bottom flask, and that will have our impure product. So that's what we're going to attach first. When we're attaching it, remember that we need to also include our water flow, so making sure that we've got that water coming in, the water coming out. We're going to place a thermometer in the neck of the flask so that the bulb sits next to the entrance of the condenser, and that's really important. It's where the entrance to the condenser is, because we don't want to be measuring the temperature at the top of this flask here, because it'll be a different temperature lower down because heat rises. And actually, when we're looking at that temperature there, we'll be reading the wrong temperature, and then we could be if because of the different boiling points, if they're very close, we could actually be distilling an impure product again, because we could actually end up by this point hitting two boiling points of two of the different products. So the temperature on thermometer will show the boiling point of a substance that's evaporating at any given time. So it's showing us what is evaporating at that point in the flask. So that's really, really important, and that's where our thermometer is. And then we are going to heat our impure product. What is really important here, we often don't talk about this, but organic products are flammable. Well, many of them are. So many organic products are flammable. So when we are heating it, we often just say, oh yeah, heat. And lots of people assume that we mean using a Bunsen burner. But because many organic products are flammable, what you should actually use an electric heater. And that just makes it a little bit safer. And that's because if there's any leftover organic products on the side, on the outside of a bottle, because of a small amount of spillage that you might not have been able to help or even notice, it stops that risk of them setting on fire because of that flammability of them. So that's just something to keep in mind. And now that we're heating the product, when the product that you want to collect boils, and we know it's boiling and it's the product we want to collect, because the thermometer is showing its boiling point, we then place a flask at the open end of a condenser to collect your pure product. And that's distillation. Distillation is really nice and simple. And And that's when we can, this is for volatile liquids, and we can purify them by distillation. So I am just going to add on that that was for a volatile liquid. So we've gone through separation for water-soluble impurities, distillation for volatile liquids, and now we're going to look at solids this time. So organic solids, and we can purify organic solids by recrystallization. So that's really important that we know that this is for organic solids. So if the product of your organic reaction is a solid, the simplest way of purifying it is recrystallization. So the first thing you're going to do in this process is you are going to dissolve your solid in a hot solvent. We do this to make a saturated solution. So this ends up making us a saturated solution. And that means that's a solution in which the maximum possible amount of solid is dissolved in the solvent. We then let it cool. As the solution cools, the solubility of a product falls. And when it reaches a point where it can't stay in solution anymore, we then get pure crystals forming. So, talking it through again, we add a very hot, and I'm going to underline the word hot because it is that important. We add a very hot solvent to our impure solid. I'm just going to make sure that we realize it's an impure solid. So to our impure solid, until it just dissolves. It's really, really, really important not to add too much solvent, and we should get a saturated solution of our impure product. We're going to filter, so I'm going to actually add on another stage. So let's get rid of some of this. We are now going to filter the hot solution through a heated funnel. And that is to remove any insoluble impurities. So in case we've got any insoluble impurities in there, we can get rid of them straight away. So we filter, so we're going to dissolve, and then we're going to filter through a heated funnel, and that gets rid of any insoluble impurities. And then we do what we said before, we leave the mixture now to cool down. So we leave the mixture to cool down, and we leave it to cool down slowly. We don't do anything to it. We don't make it cool down any quicker. We leave it to cool down slowly. As it cools down slowly, crystals will form as it cools down. So the final bit that we're going to do, so we get crystals forming here, they might not be fully pure because we might have some liquid still on those crystals. So what we're going to do is we're going to remove the liquid containing the soluble impurities from the crystals. So we remove the liquid which has soluble impurities from our crystals. We do this by filtering, but it's not just normal filtering. We filter the mixture under reduced pressure. How we do this is we pour the mixture into a filter paper lined in a Buchner funnel. So I'm just going to pop on that we do this in a Buchner funnel here, just to help. So we filter under reduced pressure. We do this by filtering Point filter paper lined in a Buckner funnel, which is a flat bottom funnel with holes in the base, and that sits in a sidearm flask, which is then attached to a vacuum line. And then our final stage is then that we wash our crystals with ice cold solvent. And that's really important, because if we have a look at the beginning, we were doing things with hot solvents. We filtered in a heated funnel, we then cool, we remove our liquids, which are the soluble impurities from the crystals, and we filter under reduced pressure using a Buckner funnel. And now we're going to wash using ice cold solvent this time to remove, and this is to remove any soluble impurities from the surface. Oops. And the final stage then is we just leave them to dry again. And that's all we have to do for organic solids, purifying them. The final thing is we can look at the purity of our organic products that we've made and actually see how pure they are. So we can use melting and boiling points as indicators of purity. So pure substances have a specific melting and boiling point. So pure substances have this specific melting and boiling point. If they're impure, so our pure substances have a specific melting and boiling point. Boiling point. If they're impure, the melting point is lowered, but, and this is really important to note, the boiling point is raised. If they're very impure, melting and boiling will occur across a wide range of temperatures. So what we can do is to test the melting and boiling points to see how pure a product is. So we can use what you can see on the screen here, which is a melting point apparatus. And this allows us to accurately determine the melting point of an organic solid. So what we do is we pack a small sample of our solid into a glass capillary tube and place it inside the heating element. So here we've got our sample, we've got a small glass capillary tube, and we put a small sample of our solid into the heating element. We've got a temperature control on the heating element, and we increase the temperature. And we increase the temperature until the sample turns from solid to liquid. And what we can then do is we can measure a melting range. So we're looking for a melting range. And this word range is really important. That's why we've got a thermometer in there. And the melting range is the range of temperatures from when the solid begins to melt to where it has completely melted. Then, once we've got our melting range, we can look up the melting point of a substance in a data book and compare it to our measurements. And as we said, impurities in the sample will lower our melting point, and it will cause our melting range to broaden because it will take longer. What we're going to do now is just go through a couple of exam questions, look at different purifying organic compounds. So this exam question follows as such. A student carries out an investigation, carries out an organic synthesis. I'd highlight this straight away because then I know that I'm looking at an organic chemistry topic. The product that he makes is insoluble in water. Okay, so we're making a product and it's insoluble in water, and it contains water-soluble impurities. So from this question, I'd be able to work out that, okay, we're talking about an organic compound, we're talking about its our product is insoluble in water, but it contains impurities which are water soluble. Just a multiple choice question, and it asks us which of the following techniques would be the most appropriate for extracting this product. Well, straight away, we've got a product that's insoluble in water, but contains water soluble impurities. So the most logical one would be separation. It's going to be separation because we can get rid of those water soluble impurities really easily using separation. Distillation isn't going to be sensible for this one because it's not necessarily a volatile substance, and we've got this water soluble impurity. We can get rid of that easiest way there. It's not a solid, so we're not going to go through recrystallization or drying. So that one would be separation, and that would get you your 1 mark. This one is a longer question, which is broken down into 3 parts. So we'll go through part A, then part B, then part C. So a scientist has produced some impure solid sodium ethanoate. Again, straight away, I would highlight that sodium ethanoate, so I know what product it is. Well, no. Yeah, what product is made. So we know it's impure. So we know it's possibly going to be a question about making this pure. Impure solid sodium ethanoate. Solid is really important to note as well. And she wants to purify this using recrystallization. She begins by dissolving the impure sodium ethanoate in the minimum possible amount of hot solvent. And the question asks us, why does the scientist use the minimum possible amount of hot solvent? So if we think back to what we've just discussed, why would we use a minimum amount of hot solvent? And that is, we want to use a minimum amount of hot solvent, and that is to make sure that the solution would be saturated. And remember, when we were talking about the solution being saturated, we were saying that saturated solution, that's a solution in which the maximum possible amount of solid is dissolved in the solvent. So we want to use a minimum possible amount, because if we use too much, it won't work. But we want to use a minimum possible amount to make sure that the solution would be saturated. And that would get you 1 mark. Let's look at the second part of this question. So we've still got, I'm just going to re-highlight some of this. We've still got impure sodium ethanoate, purify using recrystallization, dissolves the impure sodium ethanoate, minimum possible amount of hot solvent. This asks us to outline the rest of the procedure that the scientist would need to follow to recrystallize solid. This would be 5 marks, so it's going to be 5 main points. So she has saturated the solution, and we saturate it in hot solvent. So we've done that part already. So the next thing that she's going to do is she's going to filter the hot solvent, and it's important that you're including the temperatures in this. So she's going to filter the hot solvent because it's going to be hot. And I don't want the word solvent there, sorry, I want the word solution. She's going to filter the hot solution. Filter the hot solution. It's hot because we've added a hot solvent to it. Solution because we've now got our impure solid sodium ethanoate mixed with the hot solvent. So we're going to filter the hot solution through, and remember, it's a funnel, but it's not just any funnel, a heated funnel, because we're wanting to keep the temperature high, through a heated funnel. And this is to remove any insoluble impurities. That will get you 1 mark so far. So that'll be your first mark. Second point then that you want to say, number 2, is you're then going to leave the solution to cool. And I'm going to add cool slowly because that's really important. Leave the solution to cool slowly until crystals have formed. Again, that will get you the second mark. Third point then, we are then going to filter the mixture under reduced pressure. That will get you another mark. Then we're going to wash those crystals with ice cold, and it's important you include that, crystals with ice cold solvent. And then the final stage is leave the crystals to dry. And that would get you the whole 5 marks. The important things I would say is making sure that you're using hot solution in a heated funnel in the first part, and that we're saying that that's to remove insoluble impurities, cooling slowly, filter the mixture under reduced pressure, wash the crystals with ice cold solvent, and then leave the crystals to dry. And then the final part of this question asks us to describe the melting point range of the impure sodium ethanoate compared to the pure product. Well, as we've said, when we have an impure product, the melting range changes and the melting point is lower. So the melting point range of the impure product will be lower and broader, and that's really important. You include that breadth there. So it's lower and broader, and I would include than the pure product because it's asking you to compare. So your important parts in this question that you've said, the melting range of the impure product will be lower and broader than your pure product. And that is an overview of purifying organic compounds.